Good morning and welcome to Analog and Electronic Circuits. This is lecture 25. So, in the last class we looked at the differential pair with an active load . And after a fair bit of analysis, we basically concluded that as far as the small signal equivalent is concerned, if this is VCM plus small vd and this is VCM minus small vd, the this node X, if you look at it, the Norton equivalent is what is the short circuit current? That is 2 gm of the NMOS transistors times Vd, and the output resistance is ROP parallel RO, right. And we also recognize that even though it is possible to get this result using fake analysis, like for instance, if you assume that the virtual ground there, I mean that common source node is incrementally grounded, you will still get the same result, right, though it just happens to be just what do you call serendipity, right. It's just like saying 11 by 22 is basically 1 by 2, right, okay. And sure enough, you do 1 1 1 by 2 2 2 and you cancel 2 of them also, it looks same. You can even cancel the hundreds place and the units place and still the everything will look the same. Just because the final answer is correct, it does not mean that the process is correct, okay. So, this is one more of those things, but it is a good thing to remember that, well, the answer is the same, so that you do not have to scratch your head when you have to find the answer. All right. So, our aim, recall, is to make an operational amplifier, and the next order of business is to get more gain, because as you can see, the incremental gain that is possible from the differential amplifier, right, is about of the order of GMRO, right, which is maybe 30, 40, something like that. And we have to increase the gain. So, we have to cascade it with, one way of fixing the thing is to we cascade this gain stage with another gain stage with again the maximum gain we can get, which is a common source amplifier with an active load, which will give another roughly another factor of GMRO. And so, if you have say 40 and 40, you basically have 1600, right, for the gain, which is respectable, right. And after that, we would the op-amp is basically, remember, a voltage controlled voltage source with a lot of gain. We have gotten a lot of gain, right, but after that we will need to make sure that we need to get voltage controlled voltage source has a very low output impedance, right. So, we need to make sure that whatever we build not only has a high voltage gain, but also has a low output impedance. It does not help to have a very large gain which which goes to 0 as soon as you load it up with some load resistance, okay. But first things first, we will have to let us just simply figure out how to get high gain, right. So, the consensus is that we need to cascade it with another high gain stage. The simplest high gain stage we know is the common source amplifier. So, the question is what kind of and we know that common source amplifiers can be made with either PMOS transistors or NMOS transistors. So, the obvious question now is, should we use a PMOS based common source amplifier or an NMOS based common source amplifier. Correct? That evidently two possibilities. Okay. So, if we use a PMOS, when we don't know, what do we do? Yeah. Well, there are only two possibilities, right? If there are 2000 possibilities, then you have to be smart about it and figure out what you will try. But if there are only two possibilities, rather than spend time trying to figure out how to be smart, you might as well try both the alternatives and then see if any of them work. I mean, it could turn out that none of them work, in which case, you have to scratch your head and figure out and look at your neighbor's question paper or answer paper, right? If both of them work, oh, it's great. So we know that there are more than one way of doing it. And if only one of them works, well, bingo. I mean, we know that only one way works. Okay, so we've started everything with NMOS, so we might as well do this with NMOS. So what I will do is basically say, okay, here is a common source amplifier. And we need an active load. So what do we do with the load? We need a PMOS current source, and I'm going to just draw this like this. Just otherwise, you have to draw, transistors in the mirror and all that. So I will just simply, what do you call? Let me do one thing. Let me call this I1, which stands for the first stage, and I2, which stands for the second stage. All right, and what do you call? I will cascade the common source amplifier. It has an active load, right? Okay, and this will give me what incremental gain when all transistors are operating in saturation. M2, M3, M4, M5. What gain will it give me approximately? Assuming all the transistors are operating in saturation, what gain will we get? Yeah, you will get an incremental gain of JMR naught the whole square, right? And what comment can you make, assuming everything is operating in saturation, what comment can you make about the output resistance looking in there? Yeah, what will it be? It will be of the order of R naught of the NMOS transistor in parallel with the output resistance of the current source. I mean, in this again, let to remind you that I2 is marked as a current source, but it in reality is going to be implemented by a PMOS transistor. So the effective output resistance looking at the drain of M5 is going to be, assuming everything operates in saturation, is going to be large. So we have a large gain, but we have a large output impedance, which is no good, because if you have a large output resistance, then simply loading the output is going to reduce the gain big time. Correct? So what do? We have a large gain, large impedance. We want to get large gain, but we want low output impedance. So what kind of controlled source will you put there? A voltage controlled voltage source. And what is the simplest voltage controlled voltage source? The common drain amplifier. So we will figure that out as we go along. But at this time, let us say a common voltage controlled a common drain amplifier is basically a voltage controlled voltage source, ideally with a gain of 1. Right. So let's assume that we somehow, we'll figure this out later. At this point, let's assume that we have a ideal VCVS with a gain of 1. Right, with the insurance that we know how to make this. All right. So this is my, within quotes, what do you call, first cut operational amplifier. We need to figure out whether this is feasible as a as an op-amp or not. Okay. Now the first thing that I'd like to point out is the following. and this has got to do with a lot of your the circuit diagrams that you're probably exposed to in the past, and you see routinely in books and papers. And for example, here is your common inverting amplifier. What is VO by VI? Minus R2 by R1. Yeah, but clearly you don't expect the op amp to work without any supplies, correct? So what is the implication of drawing this picture? So if this is grounded, correct, this must be VDD, and what comment can you make about the negative rail of the op amp? Can this be 0? Well, here is a power source for the op amp, so it seems kosher, right? So is this okay? I mean, if you didn't know the internals of the op amp, I mean, I won't blame you for not knowing this, correct? But now we do know what goes into the at least the first stage of the op amp is a differential pair, like the one shown on the on the left, correct? Now the question is, can this be ground, and can the negative rail also be ground? All right, we don't know. Let's try to figure it out. Okay, assuming it was okay. All right, assuming that the positive supply rail of the op amp is VDD and the negative rail is ground, which is 0. Let us see if this inverting amp works. Correct. So for example, if if the op amp was working, what does it mean to say the op amp is working? It has got. What does it mean to say the op amp is working? Yeah. So the easiest thing to figure out whether the op amp is doing its job is to measure these two voltages and see if they are the same, right? If that is ensured, then all this R2 by R1 everything will follow, correct? So if this op amp is working, what comment can you make about that potential? That potential is 0, okay? This potential is also obviously 0, correct? So so if you go into the op amp, the first stage, you are going to have a differential pair, correct? So this voltage is 0, this voltage is 0, correct? Okay, if the negative rail is also 0, what comment if the op amp is working, all transistors are operating in saturation. If these two input nodes are 0, what comment can you make about that voltage? What is the current flowing through M1 and M2? If the transistors are operating in saturation, what are the currents flowing between M1 and M2? I mean, in M1 and M2, I1. If I1 is flowing in M1 and I1 is flowing in M2, what comment can you make about that source node, common source node? It will be minus of Vt plus some delta V, where delta V is the overdrive. Okay. Now look at this current source, how it must operate. It must pull current from a node whose potential is lower than the other node, correct? So is it possible? Is it possible or no? It is not possible, and therefore the negative rail cannot be at ground. It must be much lower, right? Okay. And so that's why so when people draw these diagrams, right, they simply show this, and a lot of students really don't understand that you cannot have this situation where you connect the non-inverting terminal to ground, and the negative rail of the op amp is also at ground. The only way this can work is if this is at some, let us say, minus VDD. Okay, that is acceptable, because if this is minus VDD, then what? Yeah. So, this basically this voltage is minus of Vt plus delta V, this is minus VDD, which is much lower, and therefore, this current source will be able to function, right. In other words, the common mode voltage that you apply to the input of the op amp, right, must be within the common mode range of the differential pair. What do we understand by the common mode range? So, basically if you keep increasing the common mode voltage at the gates of M1 and M2, they will eventually go into the triode region. If you keep pushing the common mode voltage lower and lower, the transistor I1 will go into the triode region, right. So, the common mode range is basically that which keeps all transistors in saturation, and clearly as you can see, if you use a negative rail of 0 and that is also 0, we end up with a contradiction. It's clearly not possible to have all the transistors, the input stage working, which basically means that the gain of the op amp cannot be, if the transistor input stage transistors don't work, what comment can we make about the gain of the op amp? There will be no gain, correct. If there is no gain, then what comment can you make about that potential there? It will not be this, it will not be the way you will not see a virtual short, right, which is a contradiction. So, we said that we are seeing a virtual short, which basically is predicated on the fact that all the transistors are operating in saturation, and we go through that line of reasoning and we find that it is not possible for all the transistors to operate in saturation. So, therefore, when people draw diagrams like this, it is understood that you have dual supplies. Alternatively, so again we come back to our usual trick. If we do not like negative supplies, let us say this is minus VDD, what do? Add VDD to all the nodes. So, in other words, Vi instead of riding on ground, right, will ride on VDD. This will be VDD, this will be ground. What will that be? 2VDD. Okay. And instead of calling this 2VDD, we call this VDD, then what will we call the other VDDs? VDD by 2. Okay. Does it make sense? So, this is sometimes called to differentiate it from this is sometimes called analog ground. Okay. All right. And as I said, it is not immediately apparent why this must be VDD by 2, right, unless you understand the internals of the op amp. Okay. There are special op amps which can basically go where their common mode range can be all the way from 0 to VDD, right, and such op amps are called what are called rail to rail op amps, but they are within quotes designed using special techniques where they recognize this problem and try to fix it. Okay. All right, but for a general purpose op amp, the common mode range will not be 0 to VDD. Okay. Anyway, so that is basically something that we have to be aware of whenever we design an inverting amplifier or any amplifier with a virtual ground, right. That virtual ground, where any of the input terminals of the op amp is grounded, you must make sure that the common mode voltage that is so developed at the input of the op amp must be within the common mode range of the differential. Is that clear?